This is October 5th, 2021, Physics 37 lab. This is the fourth lab, projectile motion. So we are going to verify the equations of motion of a projectile by using the equipment that I'm going to describe right now. Okay, so, but before you go to the experiment, let me make an announcement. The report for Lab 3 is due next Tuesday. I'm going to give you a little bit more of time to prepare the report. So it's now due on October 12th. Don't forget to label both the Excel and Word documents with the proper format, right? Y here in this case is going to be your group number. Now I want you to download the Excel file if you already don't have it in your hard drive. Download it from my shareable folder in my Google Drive. Here you go. Here's the shareable folder. Here's the document that I need you to download. I'm going to download it for you. Here you go. Look for this document. And I need you to relabel that as well. Instead of Thursday, it's going to be Tuesday for you, right? The lab is going to be 04, and you put your group number, either 1, 2, 3, 4, 5, 6, or 7. In my case, I'm going to put my group number as being 0. So here you go. I'm going to open this document, and we're going to work with that very soon. Lab number 4, right? There are the tabs here below. So since you are taking the lab on Tuesday, relabel it as Tuesday L04G, your group number. Again, today's experiment is projectile motion. What we are going to do, we are going to verify the equations of motion of the projectile using actual data collected in the classroom. And we're going to find out what the spread of this data with respect to the calculated position. Okay, everything must be done in terms of SI units, meter, kilogram, second, and their combination. Okay, the equipment. Okay, spring-loaded gun. I have the spring-loaded gun here for you. I want you to put the spring-loaded gun over the table, over the top of your table, and that is the projectile launcher. It's a gun that's loaded by a spring, and in the process we can launch a projectile. You're going to need a bubble level to level the spring-loaded gun. Okay, and that, here you go. That's another equipment that we're going to be using. I'm providing you with a spherical projectile, a steel projectile. And by the way, this is the most dangerous experiment that you can do throughout the whole semester, okay? Don't get yourself hurt with the projectile. And exercise caution with that. I will walk you through how we can do that. We may need to move the tables to get some space in there. I will guide you through that. Here you go. Put the projectile at the tip of the launcher. If you want to, right now the launcher is not loaded. It's not spring loaded yet. If you want to load the spring, you gotta put the projectile at the tip. It's easier to have a large surface area there for you to load the gun. So with the projectile at the tip of the gun, you can load it, and you're ready to fire this projectile. Stay clear from the path of the projectile, okay? But before we do that, here you go. You're going to use the photo gate. Photo gate and an accessory of this photo gate as well. You're going to position the photo gate at a given distance from the projectile. You want to give a little distance from the tip of the projectile whenever it's not spring loaded. Like I said, you want to load the launcher, and then it's easier to load the launcher when there is no photo gate in front of it. But make sure you position the photo gate so there is a little bit of space between the unloaded the unloaded launcher and the gate, okay? So keep that in mind when you position your photogate. Don't put it too close. Just give a little bit of a distance, maybe 5–10 centimeters. And I'm going to place the second photogate, the photogate accessory, in front of the launcher. Measure between the distance between the gates with a ruler. Okay. And make sure you anchor the photogate on the table with a masking tape, so you are sure that those gates are not moving, those photogates are not moving, and the distance remains the same all the time. What are we doing here? We are going to measure the time that the projectile takes to move this distance between the two photogates. That's what we are going to do. In order to do that, we have to set the photogate to pulse, not gate, but to pulse. Okay, this distance divided by the time measured by the two photogates is going to be the velocity, the initial velocity of the projectile. So set it to pulse, align the photogates with the path of the projectile. That's the most difficult part of the experiment, to align the gates with the path of the projectile. Make sure you have enough of a distance here so you do not knock out the photogate when you are loading the spring gun. Okay? We are going to fire the projectile 10 times after you have adjusted the height of the photogate. You're going to fire it 10 times and determine how long it takes to move between the two gates. Okay, so let me show you the spreadsheet. Here you go. You measure the distance between the photogates, and you're going to fire the photogate, the projectile 10 times. You're going to measure how long it takes for the ball to go through the two photogates. Take the average. Okay, that's the sum, and then take the average. Okay, that's the average time, and that's going to be the initial velocity that you're measuring. The measured velocity. So here you go. Here is the data. Here is raw data. There is one more raw data here I'm going to talk about. Here is just an average of those 10 measurements. This T here is just an average of those 10 measurements. What's next? I'm going to calculate the initial speed, which is the V0 there in my chart, my Excel spreadsheet. Remove the photogates. You're not going to need the photogates anymore. Now, once you fire the projectile 10 times, you're not going to need the photogates anymore. And then you can get data from the other things as well. One thing that you're going to need is the height of the projectile. The height of the projectile, why not? It's measured from the bottom of the projectile to the floor. Okay? So here you go. This why not goes right in here in this table. I'm going to put a why not there. I didn't put it. Subscript. Here you go. Don't forget to put the units, right? What else do you need? You're going to get a plumb bob to determine the origin of your x-axis. Okay, the plumb bob must pass through the center of the projectile. Mark this position with a tape, which is the origin of your x-axis. Okay. Tape a white paper to the floor at the position the projectile lands. The projectile is going to land somewhere. If the projectile lands somewhere around here, you're going to tape a white paper at this position here on the floor. Okay. And then you're going to lay a carbon paper on the top of the white paper. Do not take the carbon paper to the floor. I want to reuse the carbon paper. Once you tape to the carbon paper becomes useless. Okay? And you fire the projectile 20 times. Make sure there is enough clearance here between the projectile and the edge of the table so the projectile doesn't hit the top of the table. Okay? The 20 data points, you are going to log them right in here. So here is our raw data as well. Raw data here, raw data here, and raw data here. 20 plus 10 plus 2, 32 data points. Okay, here's the average of your time that it takes for the projectile to cross the photo gate. The velocity is going to be the distance between the photo gates divided by the amount of time. And then that would be our predicted range given by the equation that we derived in the classroom. 2h over, here you go, h32 v naught square root of 2 y naught divided by g. Okay? That's going to be the range. Then you fire. Okay. You're going to take the average. Here you go. Here is the predicted range. What you're going to have here is the average of the experimental values. You're going to compare that with this value here, with the predicted value. Then you're going to calculate the standard deviation. It's already calculated there for you. What you have here is the percentage difference between your average experimental values and the predicted one. Should be very small. And then we're going to do something else. We are going to get those values and sum with the standard deviation. Sum and subtract. Okay? Sum and subtract. And then you sum and subtract with twice the standard deviation. Okay? What else do you do? Well, you do the following. This data here, you're going to order them from the smaller to the largest value. Okay, you can sort that out using the data here. Sort from the smallest to the largest value. I suggest that you highlight those two, so you know that. Also change the number format. This one doesn't need to have second digits, right? Can be put in red. Quantity. Nope. You're going to put them in numerical order. And then what you're going to do? You're going to count how many data points you have between x minus sigma and x plus sigma. Should be somewhere around here. Here's going to be your minimum value. Here's going to be your maximum value. But they're going to be very close. So maybe it's going to lie somewhere around here. Count how many you have. And you log right here, number of data points between x average plus and minus sigma. Then you do the same for the minus 2 sigma and plus 2 sigma. Minus 2 sigma, identify a value that is in minus 2 sigma, just above minus 2 sigma, and identify the value that just below plus 2 sigma. You count and you log it right in here. The theory predicts that you should get around 67% here. You should get like 95% here. That's what the theory predicts. Okay? So let's go through here. Here you go. That's the list of equipment: spring-loaded gun, bubble level, spherical projectile, photo gate and photo gate accessory, ruler to measure the distance between the photo gates, masking tape. Don't forget to select pulse in the photo gate. Meter stick, plumb bob, white paper, carbon paper, meter stick. Okay, we already have here meter stick. Used to measure the range of the projectile and its height. Used to measure the range and height. Of the projectile. Here's the equations of motion: x equals v naught xt. That's what we are calculating using the two photo gates. D divided by t, right? Here is the y equation for the vertical position of the projectile. In order to calculate the range, what we have to do? We have to solve this equation for t. Okay? In order to solve this equation for t, we have to set the final position at 0. That's what I did here. And that the initial velocity along the y direction is going to be 0. That's why you don't have the second term in t. So for t, you get that 2y naught over g. The range, you substitute this t right in here. Okay? So don't forget to get the significant figures. And here are the equations for the average. Here's the equation for the standard deviation. Here's the procedure to find out n between minus sigma and plus sigma, and between minus 2 sigma and plus 2 sigma. Already explained that to you. And that's what we have for today. I'll help you out performing the experiment.